face not show up there, you can turn off a camera, but we also encourage you to keep your camera on if you're comfortable. So with that on, Chris, it's all yours.
Thank you so much for that intro, and Anna and Jack, thank you for the invitation to speak with you all, and thank you to everyone for joining me this evening. Also have some colleagues I see here. Jet, it's good to see you again. It's been a little while, but I hope you're doing well. Let me share my screen here. Okay. So I'm going to talk about what I've kind of dubbed as the curious case of the smart home. I think there's sort of this interesting interplay between what we've been promised for smart environments and what we've been delivered. And I'm going to try to sort of unpick that a little bit through the lens of research projects that my lab has undertaken. I'm a computer scientist living in the Human-Computer Interaction Institute at Carnegie Mellon University. And inside of that department is I run a group called the Future Interfaces Group, which has that broad purview to think about what the future of interaction is going to be. And as Anna mentioned, I also have a startup on the side called IxDA. They're based out in East Liberty, and they're working on machine learning technologies, especially ones that power interactive functions on today's computing devices. And all kind of total, all their innovations put together, I think their software is running on something like 400 million phones as of last quarter. So pretty big install base for interactive functions. In terms of sort of my process, or sort of the kind of the things that I bring to bear to think about how to innovate on new UX, it mostly centers around these three kind of recurring themes. So sensors and signals, how do we get interesting input into computers? And then also, once we have those signals, how to use techniques like machine learning and computer vision to make sense of those signals. Accelerometer data alone isn't that interesting. We need to be able to interpret it in a meaningful and reliable way for it to be useful. And then finally, and probably very similar, to many of you, there's often an aspect of physical prototyping. If you're trying to simulate the car of the future, you're trying to think about what's beyond smartphones, you have to build that thing. You can't just show a prototype on a laptop screen and say, imagine you're holding this thing, or imagine you're using this thing. And so we often build either electronics prototypes or physical mock-ups of environments to explore the context and how users might utilize these technologies. And then in terms of sort of an ethos, is we often approach problem domains in human-computer interaction sort of asking the following, which is, what are the computational ingredients that we might be missing that allows us to sort of bake whole new computing experiences, or at least better versions of current experiences. And we take this mindset because obviously it takes a lot of ingredients to bake a good cake. And in the same way, we're drawing on advances from other fields, whether that be AI or cloud compute or sensors or natural language processing, is we're taking all those existing ingredients, then we're sort of sprinkling in our own magic ingredient, and that is unlocking or enriching an existing computing experience. And to kind of set the stage as well, as I want to play a clip from the 50s, or the 60s rather, talking about Sketchpad. So if you're not familiar with Sketchpad, that's not super important. It was an early CAD program, but I wanted to listen how, in this case, this professor called Professor Coons is describing the system.
But little by little, he will begin to investigate ideas, and the computer and he will be in cooperation, in the fullest cooperation in this work.
Well, now, how is this different from the way the computer has been used in the past to solve problems?
Well, the conventional way, the old way of solving problems with the computer, has been to understand the problem very, very well indeed, and moreover to know at the very outset just exactly what steps are necessary to solve the problem. And so the computer has been, in a sense, nothing but a very elaborate calculating machine. But now we're making the computer be more like almost like a human assistant.
So the reason why I play this clip, and it may seem kind of odd for a computer scientist to draw kind of inspiration from historical clips like this, but we often look in my lab at trajectories in computing. It's a way to project into the future by looking at the past. It doesn't seem, that complicated, but very few computer scientists seem to kind of look kind of retrospectively. And what's really interesting about this clip, and this, for those of you not familiar, Ivan Sutherland, he did his undergrad at CMU, later won a Turing Award for advances in robotics, was one of the pioneers in virtual reality, but the Sketchpad system was really influential and worth taking a look at if you haven't seen it before. But just out of that short clip of Coons describing Sketchpad, is it sort of underscores some really interesting little things. So let me just talk about these two snippets. the first quote that I think is really interesting is talking about the old way of solving problems, right? And that is the computer, you use a computer to, in order to use the computer, you have to understand the problem very well. So at the outset of your kind of using the computer, you know all the steps that are necessary to solve the problem. And if you think about it, and if we're sort of honest with ourselves as kind of HCI and UX professionals, this is really how we use computers today. We use them as tools to get things done. You know, if we want to look up how to make French toast, we know where to go, we know what to do, we search on Google, we pull up a recipe, we do it. It's fairly mechanical, even though that is an ill-defined task. The fact is we approach it and solve it in a very mechanical way. And most of the things that we're doing on computers, I would say, are mechanical, you know, and even in a very similar way to how you might go build a house or even do something, you know, creative like painting, you know, a new piece of art. And there's a process that you go through with your set of tools, you know, whether that's hammers and power drills and paintbrushes and so on. But the second quote that I've highlighted at the bottom here, I think actually hints at something a little more interesting, a little bit deeper. And that is that the computer and the user is going to be in the fullest cooperation. And what I like about this is that it's not how you describe a tool. When you have a hammer or a paintbrush, you're not cooperating with the paintbrush, you're not cooperating with a hammer. And so this is sort of hinting, this notion of a cooperation is hinting at something much more sophisticated. And, you know, he ends, Professor Coons ends it saying, it's going to be much more like a human assistant. And if you kind of play this video through, it's quite a long video, you know, that was filmed back, you know, it's kind of a publicity piece, is later they actually describe the computer, not as a tool, but as a coherent partner. And I think that's a really wonderful term. And it's, you know, echoed by many other early pioneers like Engelbart and Bush and Licklider and so on. And so I think we are still in very much this computers as tools mentality. And that's like Babbage all the way to now. And I think it's really interesting to think about, well, what does it mean for a computer to be a partner, you know, a coherent partner in a task, or an AI that's, you know, helping you, you know, prepare dinner. And this is very much the future. We are not there yet. You know, even the smartest smart assistant, Alexa, Siri, whatever, they're nowhere near computers as partners. So if we kind of go back to the kind of lab ethos, how we're attacking this problem, we would ask, you know, what's the missing ingredient? Why don't we have computers as partners? What are we missing in that, you know, to kind of bake that cake? And one of the things, and the thing that I want to talk to you about today, is this notion of context awareness. This is a fundamental missing ingredient to be able to kind of enrich those experiences. So, you know, you may not be familiar with this term, but it's very much like what you would imagine from a human, and that is to be aware of one's surroundings. So not only the physical context, like you're in a kitchen, but the social context as well. Are you surrounded by family or friends or so on? So, you know, here's some example contexts that are very different. You might have, you know, a student that's at home trying to finish an assignment, focusing really hard, a business person in an office trying to close an important deal, you know, a frustrated driver sitting in traffic, all the way to a family dinner. So these are very different physical spaces with varying constraints, and also very different social settings as well. And I would ask you, right, if you had a personal dedicated human assistant, let's just say we were all rich enough to be able to have someone like that and wanted to have someone like that, would they act or react differently across these different contexts? And I think we would all agree that yes, they would act differently. They'd modify their behavior based on these contexts. For example, they might get a piece of news that's relevant to you, but they might, you know, withhold it until after you finish your homework because it's just not that critical. But if it's related to dinner, right, and you're sitting at the dinner table, maybe it's a guest that's running late, or there's, you know, food burning in the kitchen, a human assistant probably would interrupt and intrude because it's really relevant at that moment in time, right? That someone's going to be half an hour late, right? And so they are modulating that behavior in a much more clever way. But, you know, unfortunately, today's computers are nothing close to being context aware. In fact, I would argue that they're context dumb. They're not very good assistants for that reason. They're great tools, but bad assistants. They actually tend to interrupt us and distract us much more than keeping us focused. And the idea of a computer kind of proactively intruding to help us when we may be going down a wrong path is total science fiction. Very few examples of that. And it's really because, or at least a critical kind of component, is that they know very little about the immediate world around them. They don't know you're having dinner. They don't know that the dinner is burning. So how can we possibly ask them to be context aware? So just to kind of, you know, hit this point home, right, is you might have a smart speaker sitting on your kitchen, you know, countertop. It's supposed to be, you know, a smart speaker, but it has no idea it's in the kitchen. It has no idea that you're making dinner, right? Despite having a very sophisticated suite of sensors and essentially unlimited cloud compute at its disposal. And then likewise, you know, smartwatches, maybe it's even more exaggerated, right? Is that you can, you know, ask a smartwatch with a voice assistant, you know, tell me the full history of Australia, and they'll just read you the whole Wikipedia article on Australia. They'll tell you the real-time traffic and weather conditions in Sydney, whatever, 10,000 miles away, but they know nothing about what your hands are doing. And they're literally sitting on your wrist, right? So there's this weird like impedance mismatch between something that should know way more about your hands than the weather in Sydney actually knows the total opposite. And actually weirdly is that smartwatches often include pedometers. So they actually know more about your feet than what your hands are doing, which is kind of a weird mismatch. So we have to think about how do we build this future from the ground up, right? We need to kind of think how we're going to achieve this vision. And there's a lot of work ahead to really do this. And I think you really need to bootstrap computers starting right at the bottom. And you need to have approaches that allow computers to sense their surroundings, on top of which you can build more sophisticated models of things like context awareness. And that's the crucial ingredient to be able to get us, or at least an ingredient to get us to this notion of computing as partners or computers as partners. And that's sort of setting the stage for telling you about some of my lab's research in this area. Now, I'm not going to go into too much depth in any one project because I want to show you the landscape of the ideas that we've been playing with. I think everyone who's joining this presentation is someone who their currency is ideas. So I want to show you breadth instead of depth. And we'll have time for questions. You're welcome to put questions into the chat as well, and I'll try to clarify them, but we'll have some time at the end as well. So to kick this off, I want to talk about a project called synthetic sensors. And the name is apt because we're trying to create sensors that are not a one-to-one mapping where you have to take some sort of doodad and stick it to your dishwasher in order for that dishwasher to be smart. So the notion of synthetic is sort of these virtualized elements that you can kind of create them on the fly. And the way that we explored this was by creating our own sensor board. So we actually inventoried a whole bunch of off-the-shelf or research or commercial offerings for these kind of sensor tags that you can buy from Texas Instruments and ST and so on. These are kind of little, often battery-powered things that you can sort of stick to things to give them some degree of smartness. And then that can feed back to something like a Siri or an Alexa or whatever your favorite assistant is to make them more smart. And we looked at what sensors they included in their makeup, things like humidity sensors and light sensors. And we said, well, we're just going to include everything that they have. We're going to literally take the union of whatever we found in industry, and we're going to include them all. But notably, we're not going to put a camera on it because obviously, people putting one of these sensors in their bedroom, they're probably going to be a little bit cautious about a camera. So we put this together. Again, not going to go into too much details, but it had a lot of different elements. Here's actually what the board looked like. So in this case, it's got a USB jack, but you can sort of imagine this is meant to just plug into a standard outlet, like imagine it all integrated together. And we're using wall power for a very important reason. One, we don't want to have people replacing batteries all the time. We actually did sort of an inventory of a house. What would you want an Alexa to know about, right? They want to know about your oven, is that still running? Is the gas stove on? Is your fireplace on? Is the laundry machine on? Is your HVAC running? And is the garage door open? Is a window in your bedroom left open? If you enumerate out that entire list, it tends to be on the order of about 100 different things. Just think about all the individual windows, individual drawers that you have in your house, every door and so on. It adds up pretty fast. And we don't want to have a battery powered thing that you have to stick on every single one of those, such that every 3 months you're running around replacing 100 coin cell batteries. It's a non-starter. So we took a different approach, which was let's just use wall power. Then we can also use as much compute as we want. We don't have to be energy sipping, or at least relatively. We don't have to run on a coin cell battery. We can do a lot more machine learning right there at the edge, so we don't have to stream all this data to the cloud and send it to people, at Amazon and Facebook and so on. But it does mean, as a consequence, we have to sense things from afar. Now we're not attached to the object you want to sense. We need to be a little more clever with our machine learning. But it turns out it's actually very possible to do. So here's a clip. So in this case, the sensor is right here, sort of behind the faucet. And you have, in this case, one of my grad students is walking around. And you can see the classification result here. It's showing you what is going on in this kitchen. So even though there was only one sensor in that room, it can actually sense everything going on in that kitchen just with a single $100 sensor board that never has to be maintained. You can plug it out of the way somewhere and it'll understand what's going on. Same with a single bathroom. There's one sensor right here. but it knows what's going on with the faucets, the shower, the toilet, and so on. And this is true for a whole host of events, both in domestic spaces and industrial and commercial spaces as well. So now instead of one sensor per object, we're more talking about one sensor per room. So if you have 10 rooms in your house, it's 10 of these boards. Still expensive, but we're getting towards more feasibility and importantly, generalizability. So that's what we talk about when we talk about synthetic sensors, is that even though they're not attached to that object, we can just create a software-defined sensor feed of, for example, is your dishwasher on or off, without actually knowing much about it. But just knowing if your dishwasher is on or off is not actually all that useful. That's a very low-level sensor. And so we can start stacking kind of these different sensor inputs into one another. So for example, we could actually have a towel counter sensor. You can't see the sensor, it's off on the slide here. So one is just saying, I heard a towel, I heard a towel, I heard a towel. But a second order sensor is actually counting how many towels have been used over time. Very basic level of abstraction. Same with this faucet running sensor here. So again, the sensor is somewhere else in this kitchen, but we can use that data about how many gallons you're using in power, something like a behavior change application on social media. And of course, even though, again, like, how many towels you've used, how many gallons you're using, you can start building those up more and more and more. And so you kind of get to these nth order synthetic sensors. So you might actually have a synthetic sensor that's called, family over for Thanksgiving dinner. This really meta specialized sensor. And it's fed from, oven activations and noise in the living room and how many seats are being utilized. And it's very meta and all put together to have this very specialized sensor. That would be something that'd be very important for a digital kind of agent, an assistive agent to know. Now, what's cool about this project, we actually started this work over 5 years ago at this point. I think 2016 is when we first made our first version of the sensor board, but the project is alive and well. And actually what's been happening during the pandemic is CMU has finished construction of this new building along Forbes Avenue. And Professor Agarwal, one of my colleagues, has actually taken our sensor board and deployed 350 of them to this building. There's essentially one of these sensors in every single room in this building. It's probably one of the largest deployments of its kind to sort of use it as a living laboratory to kind of explore the notion of what does it mean to actually have a smart building? Because we've been hearing about smart buildings for a very long time, and they're really very rudimentary. It's like room occupied or not. Are the elevators going up or down? Very basic. We want to have it really be fully kind of sentient in some respects, or fully aware of what's going on. So leading from that past work was because we included all these different sensor channels on that board, is we could actually say, well, what sensors are more useful than others? Like we had a humidity sensor, we had a microphone, we had a light intensity sensor, a light color sensor, but we could do this analysis with the kind of power of machine learning, saying, well, can you rank order those for us? What was the most useful for figuring out what's going on? And what was the least useful for knowing what's going on? And it turned out that there was two sensors that really were tremendously useful. And that was microphones, so basically listening to the noises going on in a room, and the accelerometer, which can actually sense the vibrations of things like a faucet running or a toilet flush. The plumbing actually causes it to vibrate, the room, the infrastructure, the studs in your wall to vibrate at very particular frequencies that allow actually for very robust classification. But what we liked about especially microphones is we realized that so many devices have microphones already. Smartwatches, smartphones, smart speakers, TVs, all these devices have microphones in them already. So could we just get away with just using the microphone alone to give people context awareness? So you can do a little experiment. I'm going to play a video next. If you want to, you can close your eyes and just listen to the sound and see if you can be sort of the machine learning classifier that can guess what's going on in these scenes. So I'm going to play these sounds for you right now. So you can open your eyes now. What we had is chopping vegetables, sort of mixing in a bowl, a vacuum cleaner, someone typing, and someone brushing their teeth. And a lot of these have very distinctive sounds. I would suspect that most of you probably got 4 out of 5 or maybe 3 out of 5 with no training data at all. And I only played them for 1 second each. And so it turns out that computers can do this too. If you give them enough training data, they can also become aware just based on the sounds. And of course, if you hear someone brushing their teeth, or if you hear a sound that's very similar to brushing one's teeth, and if you know your location, I'm in a bathroom versus I'm in a kitchen, you might make the inference that they might be scrubbing dishes. So again, context lets you disambiguate quite a bit more than just the raw sound alone. And so we thought about, well, hey, why can't we have something like in the setup of an Alexa, like a drag and drop interface like this, where we can say, okay, Alexa, you're in my kitchen. I want you to listen out for doorbells and smoke alarms and the chime of my microwave, and when my stove comes up to, my oven comes up to temperature, it makes a very distinctive thing, and I want you to listen for all these things, baby crying, doorbell, whatever, and then it just becomes aware of those and can do proactive things based on that. And we like this idea of a user defined, so they're not listening to everything in the environment. Obviously, we want to minimize that as much as possible, but to be reactive to things that we think are high value. And so kind of taking this a step further and thinking about other applications, you might imagine, for example, health sensing from a smartwatch, that if the smartwatch can hear that the user is coughing more than usual, maybe that's time to go in for a COVID test or something like that. And again, this is popping up automatically. It isn't like you have to launch an app. Here's like an industrial kind of use case where we have, again, in this case, we have a laptop here, but this is mostly for illustration. You might have a little sensor in that room, and it's listening to the utilization of all those tools, and it's keeping a runtime to see which ones might need service. You can see the CNC milling machine here has been 34 hours since its last service. Maybe someone should go check it out, grease it up, whatever it might be. And here's another example. I actually think this is one of my favorite sort of mini vignettes of an example, is someone operating a drill press. And as soon as the smartphone hears that drill press, it says, safety first, don't forget to wear your safety glasses. They'll say, okay, I'm wearing my safety glasses. And because it knows it's a drill press, it'll actually estimate the RPM of that machine and says, this is ideal for softwood. So if you're cutting acrylic or something else, it'll actually make a recommendation for you. And this is your smartphone preemptively waking up out of a off state to make a recommendation, right? So this is sort of like, you're at the end, when you're in the office again, you're heading home from work, you start that car, your smartwatch automatically turns on and says, don't take Penn Avenue, or stay away from Route 28. There's a big accident, right? And proactive as opposed to being always reactive. So the way we did this whole project, in order to get enough of these kind of sounds, is we actually used Hollywood sound effects. There's a lot of people in the kind of machine learning AI community that are trying to train these enormously complicated systems, these models, using things like YouTube as a data source. But the problem with YouTube is, I can type in Blender and I get 5 million videos of Blender reviews and people using blenders. It's really unstructured. What we found is that Hollywood and a lot of the licenses that CMU has for their film and kind of drama departments, theater departments, is they already had great curated sound effects, very nicely recorded in professional studios with really high quality microphones, that we could actually go to one of those licensed sound effect sources, type in Blender, and we got like 1,500 beautiful Blender soundtracks. And we could actually remix those in different ways. We could speed them up a little, we could slow them down a little, we could superimpose them into different synthetic environments, like an echoey like kitchen with like a tile backsplash versus a big kitchen with lots of wood. And we could actually, from those 1,500 Blender sounds, we could transmute it into tens of thousands of different Blender kind of sounding like things to train a very complex model. But what's really interesting about a general approach like this is that it's never as accurate as actually your own blender. Like, it doesn't matter how many blender sounds I throw at it, your blender in your kitchen always sounds a little unique. And for that reason, it's very hard to get this up above about 95% accuracy. From users expect 99.999% accuracy. So 1 in 20 is not going to cut it. And 1 in 20 errors is not going to cut it. So we kind of revisited this last year with a system called Listen Learner. And the idea was, why don't we just have, these smart speakers are sitting in environments, or your smartwatch is going with you during your day. Why don't we just have it listen, almost like a baby, listening to the sounds around you? And, it can tell when, some things like typing sounds very different than a microwave chime. It can sort of cluster these together. And when it knows, I don't know, it is like a running faucet sound, but when I've heard enough of those, I can prompt the user saying, teach me what that sound is. And you'll say, oh, that's my faucet. And then it's learned what that sound is. So here's an example of that. So here's a Apple HomePod sitting on this countertop. There's someone chopping, and we have a little visualization here. It shows you the sounds being recorded. So here's kind of cutlery sounds. They sound very different than chopping. So they're kind of getting projected into a different spot. And then the user kind of goes about their time making lunch or something. And you'll see there's another little cluster here. This is the microwave running, kind of a humming sound.
the microwave.
You'll see here now this cluster turned pink. So it had picked up maybe like whatever, 3 or 4 minutes worth of microwave humming sounds. It didn't know what it was. It knew it was its own thing, but it didn't know that it was a microwave. So it just asked the user. It had enough data. It said like, I know this is a thing. It's very separate from these other kind of clusters. I'm going to now intrude and say, can you teach me what that is? And now I've learned. So like your doorbell almost certainly sounds different from my doorbell. Very hard for it to recognize all doorbells on the planet. But after you turned your doorbell 10 times, it's not like that sounds like anything else in your house. It should be able to learn it and at very high accuracy. And if you let this run long enough, you start to build up clusters like this. Now you might say, hey, but Chris, look, there's like overlap. And there is always some overlap, but this is a very low dimensional projection, they would say, of a very complex space. I'm projecting it into 2D, but imagine this is in 3D. So there's sort of a Z-axis. And actually in reality, it's more like 50 dimensional, which unfortunately I can't show to you. And if someone wants to work on that problem, that'd be very cool. But this gives you a little bit of an intuition about how we're clustering. A little bit of a kind of just a bit different, but also something that we tackled last year is thinking about direction of voice. So, if we were all in person, and I hope I get to meet some of you in person at some point when we're back, together again, is how you address humans in a conversation. We actually think about which way you're pointing your voice. You both look at people with your gaze, but you also send your kind of voice to things. So often when people are talking to a smart speaker, they actually turn and face it and address it in a very kind of anthropomorphized way. Not always, but generally that's how we think about human-human communication. And that's not what we actually see in today's devices. So if you kind of extrapolate out, thinking about an ecosystem of smart devices in the future, you might have a laptop and a smartphone and a smart, exercise bike and a game console and a smart TV and so on. And if you ask a question like, what time is it? The problem is that they're all going to respond because they don't know who you're talking to, right? A human wouldn't make this mistake. If a person was facing towards a human and say, hey, do you want to go get lunch, or what time is it? Only that human would respond, not someone who's standing behind you. And so if we could get this kind of vector of direction of voice, along which line people are projecting their voice, that'd be a very useful social contextual clue that we can make smarter interactions. So if I say, hey, what is the time? Only my smartphone is going to respond. And then likewise, if I tell my laptop to play music, only my laptop will play music, and so on, right? So I'm not going to go into too much technical detail, but we were able to get this working. So what you'll see in this very kind of very basic demo is we have sort of our stand-in for a smart speaker right here. And again, just a laptop for illustration. And it's trying to guess the angle at which that person is talking to it. So talking directly to it is going to be 0 degrees.
When does my bus come? When does my bus come? How is it outside?
So again, it's trying to predict. And again, maybe the device will actually ignore commands that are at any other angle other than 0 plus minus some percent. And it may even be that in the near future, we can dispense with wake words. Right now we have to say, and I don't want to say anything, but the other word for Siri and Alexa, everyone's apartment's going to go like crazy. But it's kind of ridiculous that when I'm literally 1 meter away from my smart speaker and I'm talking right at it, I still have to use a wake word. Like, again, these are supposed to be smart devices, but yet I have to do that every single time. And if anyone's ever tried to use one to move through a recipe or like a cocktail recipe or something, it's excruciatingly painful and not like human-human interaction because it's just so awkward. It's just so awkward. And little tiny, again, like kind of thinking about the ingredients to make these interactions more natural, more fluid, faster. This is the kind of stuff that we need to bring to bear. Another example, this is a bit older again, but thinking about walls, like, we don't want to necessarily have to stick these kind of little ugly electronic things everywhere. Can we sort of give the walls like an upgrade? Can we make them the smart element? And the way we thought about doing this is actually essentially like a wallpaper. In this case, we're painting it. So we just do this with off-the-shelf stuff, painter's tape. And what you can see, this is some Ph.D. students again, they're laying down a very particular pattern. That's the sort of this diamond crosshatch pattern that can go inside your wall. So it actually kind of is part of the fabric of your wall, but it could even be pre-patterned onto drywall, for example. You could just buy smart drywall. And essentially what these walls are touchscreens. So in this case, they can actually sense when a user is close, and they can, of course, do touch interaction. So for probably less than $1 extra per a square meter of drywall, you can actually have full touch and gesture interactivity baked right into your walls. Again, like from the factory, just kind of do the drywall as usual. If you're close enough, although unfortunately you have to be pretty close, as you can see right now, I can even try to guess the user posture. But the other cool thing that we found is these can also act as antennas. And so we found that when you're running electrical appliances in a room, like a hairdryer or a power drill, or when you touch the touchscreen of like a tablet, is you'll see here the signal is very distinctive. So there's this big resonant frequency. It's actually the refresh rate of the touchscreen running. And the walls can actually kind of listen to the electromagnetic interference. All electronic devices are essentially little tiny radio stations. The FCC makes them so they don't broadcast very far. So when you're running like your hair dryer, it isn't, no one can listen to the radio for 5-block radius. They only, emanate at any reasonable amplitude for maybe 10 meters. But it's very rare to be more than 10 meters away from a wall unless you live in a gigantic house. And so the walls can actually be a smart part of the sensing infrastructure to listen to your appliance use without having to attach any kind of new sensors to these kind of devices. Another project, again, I'm trying to go breadth here, and again, feel free to ask me any questions about these projects. So another project is called Surface Sight. Same sort of concept is we said, well, hey, look, a lot of these smart devices are sitting on surfaces, right? They're not levitating in the air. You have like a Nest thermostat attached to the wall. You have a smart speaker or a conference room, sitting on a table, sitting on a countertop. And so what happens if we kind of snuck in some extra sensors that allowed us to use that surface area, use the wall or use the tabletop as an interactive medium to make them a little smarter? So as one very kind of basic way to kind of prototype this is we just got an off-the-shelf spinning LiDAR. This is not how you do a commercial product. It's a bit too expensive, a bit too kind of goofy, but a solid state LiDAR or depth cameras are right around the corner. They already sort of exist. And so you can imagine in the base of your Alexa, in the base of your Google Home, there's a little sensing strip that's actually looking out in a plane, sort of like a radar view, and it can see what's going on. And what you're seeing here in this sort of debug view is it can see the contours of things. So a hand looks very different in its contour than, for example, a box of cereal. And you can actually see we're able to classify what these things are on this countertop. And it turns out we can do this for a huge array of objects within about a 2 or 3 meter radius of a device. So this is sped up just to show you sort of the breadth of things, but it turns out, interestingly, much to our surprise, is there's very few things in a kitchen that are of the exact same diameter. There's a lot of like round objects, but very rarely are they exactly the same diameter. And LiDAR, fortunately, is also very accurate. They're used in, for example, self-driving cars. The technology is coming down, the accuracy is improving. And so this kind of recognition is very close to reality. And of course, we have other special types of objects. So a human contour, like us at our waist, is very distinctive. We're not perfectly round, for example. We can actually learn what those characteristics are and actually see, is a human approaching an Alexa? So as I walk up to a smart speaker, again, I don't have to say a keyword. It knows that I approached it. It knows I'm standing right in front of it. It can automatically wake up and listen. And even more so is we can even estimate the angle of the person, again, not using any voice. This is just using, again, that kind of contour plot to be able to look at, are there multiple people working at this table? If it's a conference room phone, maybe it's actually going to adjust its sort of beam-forming microphones to be able to provide optimal kind of acoustics for all the people and where they're located, et cetera, et cetera. So here's just some really quick interaction demos. Again, we do a lot of kind of physical prototyping. These are mock-ups. They're not like full-blown applications, kind of simple applications, but you can imagine a Nest not having to have a touchscreen. Instead, the whole wall is the control. I can, for example, swipe and I can change the dimmer control on my whole wall instead of having to use a really small touchscreen or have to have a very large touchscreen in a product that's going to add to the cost of that product.
Please retrieve your mortar and pestle. Next, crush 12 ounces of almonds.
How many ounces in this?
There are 8 ounces in 1 cup. Crush 12 ounces of almonds.
So what I like about this demo is it's actually, I'll just pause this for a second so I can explain, is that it's actually thinking about a different way to do event-driven programming. Like right now, all of our kind of notion of event-driven UIs is like on mouse click, on button, on page load, right? All these kind of like JavaScript kind of classic things. We don't have a notion of like building interactivity around object level things. So this was, on mortar down, on mixing bowl up, on the blender, touching the surface. Or I like the example where they shake the measuring cup, the 1 cup measure, and you say, how many ounces in this, and it resolves what this is, like a human assistant would. It knows the last thing you touched and manipulated was that measuring cup, and it can do, translations for you automatically. So it's kind of rethinking this kind of programming of event-driven interactions.
Mix ingredients together for 60 seconds.
So again, there's actually no user voice interaction at all. And like, this is just something we don't see in these current kind of voice agents. Okay, so another really important thing to think about is, how do we get to be warm? Everything I've talked about so far is about putting technology into your home, attaching it to walls, putting it on your kitchen countertop. But of course, if you came over to someone else's house, they may not have that kind of infrastructure, or they may not be willing to share it because of security reasons to like your phone in your pocket. So they're sort of context dumb as soon as they leave the confines of your home or maybe your office. And so one way to think about mitigating that is by going to warn sensing, where you kind of bring your sensing, everything you need, along with you. And so this is something that we've been thinking about. It's harder in some ways and easier in others. One of the projects this is one of the oldest projects that we've done in this space is called mSense or EMSense. And the idea here is that, going back to what I mentioned before, is that every time you have an electrical appliance, it's acting like a little miniature radio station. If it uses electricity, it has this effect. And when you touch that object, it turns out that you become actually an antenna for that object. It radiates into your body, not in any kind of dangerous or harmful way, but basically you become an antenna for that object. And if we have a smartwatch worn on the body, we can actually detect those signals radiating up your body, what's called like an RF waveguide. And so here is an example of that. So what you see on the laptop are the signals being detected by this smartwatch. And if you kind of look at this, is basically a spectrum. So what you're seeing is the frequency components of all these different devices that I'm touching, and you'll see that they're quite distinctive. I mean, they're not intelligible to humans, but you can see that they look different from one another. All these tools have their own unique motors, their own unique operation. They have little tiny processors inside of them running at different frequencies, and all those help for us to build up a catalog of all these signatures such that we can uniquely detect the moment a user touches an object, touches a vehicle, touches a blender, touches a stove, whatever that might be. And again, that can proactively power applications. So here's just some examples of that. So in this case, a user is starting to brush their teeth with an mechanical electric toothbrush, and the smartwatch automatically has launched here a 60-second timer to encourage good dental hygiene. You don't have to open up like the Sonicare app, it just launches. Here's a weighing scale that does your BMI. We can sense actually things through your feet as well. In this case, it automatically launches the person's weight history over the past month preemptively. And you can also think about patterns of activation. So in this case, the user touched the refrigerator, they touched their stove. It's 8:30 in the morning. Maybe they're making breakfast. Do you want to play your favorite podcast automatically? And here's another example. This kind of goes on for a while, but when they touch their office door, it automatically knows, okay, I'm in the office. He's just about to walk into his office. You have a meeting in 12 minutes. You have 12 emails outstanding, etc. Again, if you're interested in any of these projects, they have much larger videos on my website, and you can download the papers and see the technical implementations as well. So in a very similar fashion, instead of using, as you might have seen from that smartwatch prototype, there was like some weird things sort of sticking out of it, extra sensors that we had to add on. But then we thought about, well, hey, the other thing that's happening with a lot of devices we use is they vibrate. And if they vibrate, can we just use the accelerometer already in a smartwatch to sense these different activities? And the answer is yes. So here's a very quick demo. So here's a smartwatch, and here's just the data being rendered on a laptop. And you can see I'm rubbing my fingers together here, and you can see that the typical 100 hertz accelerometers you see in smartwatches is not very distinctive. In fact, now that we're running the motor inside this toothbrush, you can see all the little tiny oscillations in this 4,000 hertz signal, but it's impossible to ever see that in that 100 hertz signal. And we also show that here, the microphone that's in the smartwatch, it's great, but the problem is even when you're not touching it, you can hear the buzzing. So its microphone is not a great channel because it sort of fills the room. Only when you touch this toothbrush do you see those little micro oscillations. And they're oscillations that are actually propagating through your body. This is sort of like using the accelerometer in your smartwatch, like a doctor would use a stethoscope. It's actually listening to the bioacoustics inside your own body to figure out what you're touching. And it turns out you can recognize a whole bunch of objects this way. They're all quite distinctive. So poise, instruments, power drills. Again, we like to always show signals with our with all of our demos. So you can, the human can be the recognizer. Chances are machine learning can be the recognizer. And so we're doing, the live recognition here on these spectrograms. So this goes on and on and on. Here's a quick demo. So in this case, there's a recipe helper on an iPad. It says, you need to beat the eggs for whatever, 60 seconds. And so it knows the user is actually mixing by using that smartwatch. And if the user stops, the progress bar stops. So that is not a smart mixer. It's a dumb mixer that we've made smart, and you have that smartwatch always with you. We also found, interestingly enough, that you can actually tune a guitar by using the vibrations that are going up through your arm. So here's like a little assistive app for helping to tune by holding, I guess, the tuning knobs on the guitar.
Hi, can I ask you a question?
Absolutely.
Did you say that the accelerometer that's built into these existing devices are adequate or inadequate, or would you prefer something that was more sensitive for the various unique situations you come across?
Yeah, that's a great question. So it turns out that pretty much all the accelerometers that are in smartwatches are actually good enough. So what you see in like these videos is it's just a totally unmodified off-the-shelf smartwatch. We haven't done anything to the hardware. But what we did do is we recompiled the Android kernel on it with a special driver that communicates with the accelerometer. We basically kind of hacked it to communicate with us at its full bandwidth. Now, to be fair, there's a very good reason why the manufacturers like Apple and Samsung set their accelerometers to run at 100 hertz. And that's mostly because they're doing things like step counting, and running it at a lower rate does preserve some battery. It's not that it's catastrophic when you go up to 4,000 times per second kind of frame rate as opposed to 100, but it does have some impact on the smartwatch battery life. Probably reduces it by an hour a day, but that's significant. Go from a 20-hour runtime to a 19-hour runtime is pretty significant. It better be a really good application to do that, or they have to make the watch thicker to accommodate a bigger battery. But mostly, I think it's because of a lack of imagination by the manufacturers. I don't think they realize that you could do this. And that's a job as a researcher, is to show people, hey, did you know that you could do this with the accelerometer that you already have in your Apple Watch? And we're talking with a lot of these companies, and they're like, oh wow, we didn't know this could happen. So all the smartwatches, pretty much every smartwatch made, could be given an over-the-air or firmware update to enable this kind of thing. But what's the missing ingredient, and one of the reasons why the smart home hasn't happened, is what are the apps you're going to power with it? What's the killer app that's going to work? Not everyone's going to care about tuning their guitar, right? That's a very specific use case. And so we need to have sort of almost like an app store of context-aware uses to really make this a powerful thing. But fundamentally, yes, they are capable of doing it. Pretty much every smartwatch shipped in the last 10 years is capable of doing these applications.
That's pretty amazing. But I just love the idea of finding a new affordance for something that already exists, and the idea of things that vibrate, which naturally happen. We just don't pay attention to how we can find new affordances for that in order to sort of interact with create human-computer interactions, for lack of a better word. That's just very, very cool.
Yeah, thanks for the comment. Yeah, and again, going back to sort of changing how we think about event-driven applications, right? Is that if you're like Samsung and you make a Samsung microwave or a Samsung fridge, is you're going to have like a on Samsung fridge on, right? Launch my app, or I don't have to, like right now, if you want to change like the lights in your home and you have like Philips Hue bulbs, you have to like launch the app and then like go to bedroom and like change the lighting, right? Like I want to be able to flip the switch. And if I look at my smartwatch, the app's already there. Like the smartest smartwatch is one where I never have to really ever click it and I say yes, because you've already guessed what I want to do. But we're quite a long way from that vision from happening. Another question from Andrew. I wonder how these sensors might be able to differentiate between pragmatic and epistemic actions. Not really a question, but this made me think a lot about something my professor Carl Fast was working on. Okay, well, that's a big question, but we can talk about that perhaps at the end. Matt says, is there a platform you currently use to bring all these events together? I mean, all this is research apps, right? So none of this is like commercial level stuff, right? Like, so I'm showing you all these beautifully composited, videos, but this is still a research project. We are not, other than my work through my startup, which is commercialized very singular applications that we could push all the way, to consumer use. Most of these are exploratory. There isn't really a framework that like you could download and start using right away, but there's certainly generalizable information and sort of the science we've done to prove that these effects exist and how accurate they can be should you, utilize them. But in terms of prototyping tools, I mean, you can see we're very Android centric. It gives us sort of the flexibility that we need to do these applications. And sometimes there's like in the case of that smartwatch, you kind of saw there's like this wire coming out of it that was running back to a laptop to capture the data. And that was a necessary prototyping trade-off. We didn't want to spend our time doing battery optimization or, Bluetooth communication. That wasn't the point of the research. And so we, decided to shortcut there and focus on the cool stuff. So it's, mixed methods. So continuing in this vein, in fact, I can show you an example where this is actually shipped. We actually wanted to follow up on this more, not just thinking about, power tools and, your hands, chopping vegetables. Those are very like explicit kind of vibrations. It's thinking about hand activities. Like, what do your hands do? Like, if they were their own beings, what do they do all day long? And so we wanted to collect real world data for this. And we built a little experience sampling application. I don't know if this is a technique you're familiar with, but, in short, it's an app that goes to bed on your, laptop, smartphone, smartwatch. And after some predetermined random period of time, 10 to 20 minutes, it'll wake up and ask a question. And in this case, it would, this watch would be off, it would wake up, and before it woke up, it kind of recorded accelerometer data, and then it would wake up and say, hey, what were your hands doing 2 seconds ago? Can you tell us what it was? Were they, doing nothing? Were you writing with a pencil? Were you washing your hands? Were you clapping? And people could basically scroll through a gigantic list of stuff and select what their hands are doing, and they could add new ones to using a companion smartphone app. And we gave this to 50 users to wear for 2 days. We had 100 deployment days, about 950 worn hours, and we collected a ton of really interesting data. And unsurprisingly, this is rank ordered here, hands basically do nothing most of the time. It's a very long tail of things, all the way down to like smoking cigarettes and, grating food. So there's a lot of diversity, but a lot of the time your hands are doing sort of one of these things, typing on a key, or at least, people like us, typing on keyboards, scrolling on trackpads, eating, gesturing while speaking, which I'm doing a lot of. And so we can actually start to build models for how these things are. So here's just some example data. Again, I always like to show data. You can see how these things look very different. Typing on a keyboard looks very different from clapping, or all those resonant modes of operating a power drill, very, very different. And you can see, brushing hair, you sort of see this kind of rhythmic action going on. You tend to kind of do it at more of a kind of a particular cadence, and we can detect that with a deep learning model. And so we can think about not just tools that you use, things that you touch in the world, but also what your hands are doing innately. And you put those things together and you start to be able to capture a lot of contextual richness. So here's an example. Again, it takes a little bit longer for us to do this. This is using, I think, actually a 100 hertz accelerometer. So this is totally unmodified. And you can see it's a little slow, and you can see it's not totally stable. It takes normally a couple seconds to sort of stabilize its guess. But it actually can detect a lot of things that are totally passive, not just vibration generating objects, but just things like using scissors and writing with a pen. And one of the applications that we thought about was washing dishes, but also washing hands, as you can see here. And this is actually something that I can say, but Apple was able to ship this as part of their update for Apple Watch. The last WWDC that happened a few months ago, they released an update for Apple Watch, which had a hand washing feature powered by at least the initial inklings of this research. My lab has a working relationship with those guys. And they were one of my PhD students, Gerard Laput, who is now working at Apple, was able to take some of these research ideas and actually wrap it up as a production model, which has gone out into the wild. So if you have an Apple Watch, you can probably turn this on. If you have a recent model, turn this on, and you're running essentially our research code in some respects. Okay, we're running out of time a little bit, so I want to sort of skip ahead. Just talk about kind of like a little bit back to kind of the history to kind of contextualize this, wrap this up a little bit. So again, sort of laying out the time frame, kind of building on my story from the beginning, is that you have to think about knowledge, right? Knowledge is power. What computers know really makes them much more valuable as assistants and as, as partners. And so if you think about sort of this progression of knowledge, not just knowledge of the universe, but knowledge about the environment, it's got a very singular progression. So in the 1940s and 50s, when computers were, the size of, a room, they only knew what was loaded into their memory. There was not really even an internet at this time. Whatever you put in, the artillery range tables or, some sort of modeling data, nuclear explosions, whatever, that's all it knew about the whole universe, whatever was loaded into its memory for that particular computation. And then as you expanded sort of into the 60s and 70s, you got to have early kind of live examples of digitization. So most notably, SAGE, this was an Air Force strategic defense system, and it was integrating for the first time real world data. It was integrating radar data and the positions of airplanes, weather, and so on, geospatial data. And for the first time, we start to see the real world getting pulled into the digital world for it to be a powerful tool. And of course, we see the early forms of sort of the internet like ARPANET. And then into the 80s and 90s, we have the real World Wide Web emerges. Computers, even desktop PCs at home, get this explosion of potential knowledge, right? It's mostly unstructured text. It's sort of Wikipedia, but they can tell you all you want about the history of baguettes, and that's great. And they also start to learn about the real world, more about the real world. We've started to digitize weather. Was one of the earliest examples of bringing in kind of real-time weather into the internet, and then also things like traffic. We got traffic sort of in the mid 90s, and we started to layer on more and more things. And those were very high value. We wanted to know about weather, we wanted to know about traffic. And then into the 2000s and really to the modern day, there's been this absolute explosion of the ability for computers to understand what's going on around them through essentially this sort of IoT revolution. Now, you're not going to build a new building in Pittsburgh without smart smoke detector systems, smart elevators, conference room occupancy sensors. All those things are connected to the internet in one way or another. It might be firewalled, so it's only used in a particular system, but nonetheless, computers are reaching out and understanding the real world like they had never have before. And I think, obviously it's a very messy kind of timeline, but if you kind of plot that trajectory, I think it's actually exponential. Like from going from the 1940s and 50s when they had like 1 megabyte of artillery range table kind of data in memory to where they are now, it seems like it's expanding exponentially. And the crazy thing about that is humans are really bad at really understanding exponentials, because if it doubles, kind of this knowledge doubles, knowledge in quotes, doubles sort of in the next 5 or 10 years, it's really hard to understand what that might be, what kind of level that's going to be. And it tends to creep up on us really fast. And so I feel like this notion of context awareness to computers, it seems so kind of intangible, so futuristic right now, but it's one of those things that might be just like in 18 months from now, it's just like a feature that everything has because it's just so, possible. And I think it's going to be a diversity of different applications, but I really do want, I have a number of smart speakers in my house, and I want to be able to ask questions like this. Right now, if you ask, hey, Alexa, is my laundry done? It'll say, what is laundry done? Right? Or I will look up laundry done on Google and give you the definition of laundry or something, right? Like totally dumb. But I think if we can get to this is sort of what I would call like level 1 context awareness. They at least can answer basic rudimentary state questions about our environment. I think like we could be there. I mean, in some systems are already doing things like doorbell and fire alarm detection. So we're right on that cusp. But maybe in another year or two, this will be much more commonplace. And then if we start to kind of build up to like level 2 context awareness, where you take all those sort of level 1 state sensors and start amalgamating them in powerful ways, then we have start to kind of move into this computers as partner era for the first time in really computing history. So with that, I will end, and I'm happy to take questions. So I can see Anna has a question here. So can you talk about teaching these systems? You showed a couple great examples asking what was that sound, but those methods require a bit of effort by the user. If the goal is to learn as many objects as possible in the environment, I appreciate the desire not to use cameras, but could you supplement the system with cameras for the learning period? Well, it's a complicated question. I think anytime you ship a consumer-oriented device with a camera, there's going to be backlash. And I think for good reason. I mean, there's I don't want to say too much about my industrial partners and colleagues, but there's a tendency, I think, for sort of lazy smart computing, right? Which is like, well, let's just stick a camera on it. And hey, why don't we just ship all the data to the cloud? Like, even though we can process it, locally, or spend $5 more for a processor that could do it locally. Let's just send it all to the cloud. And I do think there's some nefarious reasons for that, which is that they want to collect all that data to utilize, right? They can, run algorithms through that to guess people's age and gender and even finer grained demographic details than that. And they are mining that almost certainly. I'm not like embedded in those companies, but I heavily suspect that's going on. And of course, there's payoffs from what they would call like fleet learning, where you're gathering just unbelievable quantities of data to train better and better systems. And that's a competitive advantage in this day and age. And what I really hope is that there's a consumer backlash. And it already is true for probably many people in this kind of Zoom room. I bet that is true already, that they're not buying devices because they don't like the sort of privacy policies attached to them. And I totally hear you. But I feel like if certain companies, and I think Apple has actually done a really good job with this, where they're really saying, privacy is really important to us, and people are, buying iPhones and HomePods because of that rationale. And I think as that surfaces more and we become more aware of how our data is sort of being used, I think that could be a differentiatable thing. But to your question more specifically, yeah, cameras I'm very dubious of. I feel like there's the danger, you should assume that everything is hackable. If it records it, it will leak at some point. Whether that's like the aliens get that data 10,000 years in the future in a post-apocalyptic Earth, like someone's gonna get that data at some point, is my opinion. So I just feel like cameras are pretty, tricky. Even microphones are pretty tricky. But in terms of teaching, it's like, yes, you have a lot of objects. You probably have 25, different distinct appliances in your kitchen. Kitchen is a particularly kind of rich set. But if they only have to interrupt you once or just twice maybe or 3 times, it doesn't actually turn out to be a huge burden. And we saw this with our users, is they actually kind of enjoyed teaching the device. We don't have a ton of data on this kind of preliminary anecdotal data, but they didn't even actually mind when it made mistakes. They're like, oh, that's kind of funny. It thought like this, whatever, like small whisker sounded sort of like a faucet. And so it would say, that's a faucet. And they're like, no, I'm whisking whatever, some eggs or something. And they would correct it. And they in kind of post questionnaire surveys, they didn't actually find that to be too annoying. If it is like, what's that sound? What's that sound? What's that sound? Every 5 minutes, sure. So there's this careful balance, kind of this dance you have to do between interruption and accuracy. But I think it actually can be done reasonably well, especially if it listens, for kind of weeks. And of course, the more people that respond to these systems saying, hey, that's my faucet, after the 100,000th person has said, that's my faucet, you probably have enough data to build a generalizable model where you never have to ask that again. So there is some, kind of crossover point. Jet has a question.
Yeah.
Oh, yeah, go ahead.
So my graduate work at CMU was in computational situational awareness, and it was really influenced by Dunn and Raby's Hertzian tales. And I'm also really interested in accessibility these days. And on top of that, I have asthma. So I've started doing, this is a very plate of shrimp presentation. I started doing something very similar in the past month or so with sensors for CO2, volatile organics, and parts per million. And I don't know, can I share my screen? Am I allowed to?
You are. I will make a co-host real quick.
Thank you. Oh. My entire display doesn't want to. Hang on 1 second. It's like I've never used a computer.
You should be able to now.
Okay, let's try it again. So I'm collecting data over time that people can't perceive. Again, this is going back to the Hertzian. Okay, so this is the new plot because I'm lazy. This is my office, and this is me. That big spike. Oh.
We're having a bit of a tough time hearing you, Jet.
Jet, we can't hear you very well, and we also can't see your screen really. So just a black screen. Maybe you can just ask your question verbally.
Hang on.
So while Jet is debugging that, I will jump to Andrew's question, which I think is a really interesting idea, the kind of incognito mode for physical spaces. And I don't know if there's an exact parallel, but I think if we can move to the model where it doesn't have to transmit to the cloud, where you're always essentially anonymous, maybe it's stored for 24 hours on your friend's Alexa that happens to be listening, but you are essentially never identified. You're not biometrically printed. It may be listening for things in the environment. Maybe it can hear that there is a human. That's like a super category. Maybe it can even tell there's 5 humans over, which is an anomalous event. Maybe, it'll change the playlist based on that, or, whatever it might do. But I think, we want to stay away from identifiable information as much as possible. That's again, there's no like right or wrong answer here. That's just my personal take. I really think we want to be anonymized as much as possible. And you should sort of own your own data. Obviously, if you visit a friend's house, they may own that data, but there should be an expectation of non-transmittal, in my opinion. And the more we can sort of digest it, like what a lot of our systems do behind the scenes is, as soon as we get the audio file, we digest it into sort of this intermediate thing that preserves the information we care about. We can tell it's, that the microwave is beeping or the refrigerator door opened and there's maybe a human talking, but we're not just keeping the audio file of, the entire conversation that happened. That's not necessary for the types of apps that we want to develop.
Okay, let's try this again.
Okay.
Zoom just went wonky on me. So this is air data, and this is stuff that we can't perceive as humans. Unless, well, CO2 is high, if you get a headache, then you die. So this is my office, which is about 6 feet from the shower, and this is me taking a shower. It's opening the door after I came out of the shower. That's spike of CO2 and volatile organics. And these dips are my HVAC system purging the air. So that's one set of things that I thought, like, how can I teach a machine to respond to this? And then the other, so this is my kitchen, and this is me getting up and making tea, and this is my wife getting up and making breakfast. So we've got a lot of data, and this is all stored locally. I'm not sending this to anyone, but I started looking at how can we do patterns to tell people, your CO2 is really high before they get a headache, before they go into some sort of medical emergency. And the reason this came up is we're designing a new house, and we're looking at the stove, and it turns out natural gas stoves are the worst thing you can have in your house, because they're completely unregulated. So I started looking at how bad is the air quality, what happens when I run the stove and everything is at exhaust fan. And I'm putting all this up as open source. I'll put it on my blog, but just if anybody else is out there interested in looking at sort of the opposite way, not in an opposite bad way, but I'm looking at stuff that we can't perceive.
So on Jet's note, I will share one other example here, which I think is kind of along the same sort of lines. I don't have this in my presentation, but it's part of the PDF, is we get very interesting signals that are very hard to determine. Like it's hard to make rules for all these things. Like Jet is noticing, when he takes a shower, humidity goes up, and you can see the, the kind of volatiles in the air are changing with the HVAC. It's really hard to write rules for all those things. And this is actually a really interesting example. So at the beginning here, we see this is some of the sensors in that multi-sensor board, which I think is what Matt is also talking about. But I'll go through this example really quick because it's instructive. So someone comes home, so we see motion induced here. You can see the temperature is cycling, very much like what Jet is seeing. So in this case, there is cycling from the HVAC. And we get these kind of weird little blips here. So what you'll see here at this moment right here, there's a blip of EMI, which actually turns out to be the microwave turning on. So microwaves run at the same frequency as Wi-Fi. So when you power on your microwave and the kind of whatever the emitter fires on, we get this big spike in electromagnetic emissions. Our Wi-Fi actually decreases in signal strength because there's now interference because the microwave is emitting lots of things. And actually right after the microwave it still runs for a bit, but there's all these kind of little humidity spikes. And what's turning out is happening is this student was making ramen for themselves. They were like stirring it, opening up the thing, closing it, running it for like another 30 seconds or some sort of pasta. And there was plumes of humidity coming out that was sort of tickling our sensor, where it was spiking the sensor. And then we also noticed here, if you look at this is the color. So we have illumination, but we also have color, what the dominant color is in the room. And if we kind of zoom in here, you'll see when there's just incandescent lights on, it's just mostly brown. But in this area, you can see it's like blue, red, green, yellow, brown, blue, red. This is someone streaming Netflix in this case, and the color in the room is actually changing different colors. And you'll also see that Wi-Fi goes down here. There's a big spike with the microwave, and it decreases here, and that's because they're actually streaming like Netflix, and so it's actually gobbling up some of their Wi-Fi bandwidth. And we saw there was lots of little patterns like this that there's no way a human could figure out every possible, making ramen in the microwave, then sitting down to watch Netflix. Maybe a lot of students, do that. And so we realized that you're going to have to build very complicated models to understand all the patterns of human activities. There's no way to model it all, but there's lots of data encoded. These sensors are seeing all this stuff, but no one's really put it all together. And that's a huge challenge. I'm not saying that's easy, but there's lots of data there that's accessible. And now you just need to start to have, again, maybe through kind of a listen learner technique, it's like, what the hell is going on? You're like, oh, I just made ramen and now I'm watching whatever, Breaking Bad, whatever, pick your favorite show, right? And it can learn over time. And when you have millions and millions of people providing that data, you can imagine building up this sort of semantic web, these patterns of activities to be able to have these devices be, and the reason why human assistant is so good is because they've lived through many of these contexts. They can understand, hey, they just made dinner. Are they going to sit down and watch TV? That's a very common kind of A goes to B kind of thing. It'd be very weird to, eat ramen and then start growing a tree. That doesn't really, go together all that often. So just, just a quick example there of things that can happen. Let me jump back to questions here. Matt, is the board at the beginning available commercially? Well, okay, it's complicated. You probably can talk to Professor Agarwal, and if you email me, I'm happy to share his contact details with him. He sort of tried to spin it out of CMU, and we do have extra boards around, so there may be, there might be one less in that building. And if you actually go to, I'll just type it in the chat here, mites.io, that's the new name for that project, and actually has a big open source component as well. And there are commercial offerings by Texas Instruments and so on that can do many of those things now. There's been actually a shift in industry to make more of these kind of Swiss Army knife sensor boards. Nahum, I hope I'm pronouncing that correct. Any future plans or prior work embedding these listening systems within environments for people with vision impairments? I mean, not personally myself. I don't really do a lot of accessibility research, but certainly a lot of my colleagues in my department at CMU do. And people are certainly thinking about kind of multi-sensor fusion systems for helping people with both vision impairments and other impairments. And actually in iOS, there's a new accessibility mode where you can actually have audio detection for things like fire alarms and other kind of baby crying, I think is also one in there. So it actually is creeping out in the product now. And again, Apple has both a development office down in the Strip District. They do mostly things like with iWork, so Keynote and all those things are all done in the Strip District. And then Apple also has a research lab right next to CMU where a lot of these kind of technologies are being pioneered. So there's a real kind of hub of talent there. Janelle is asking, I'm seeing this research in the lens of remote patient monitoring. A huge pain point of RPM. I don't know if I know what that is though. A remote patient managing, okay, it's remote patient monitoring. Is compliance with wearables. I see acoustics can detect coughs. I'm assuming wheezing, sneezing. I mean, yeah, to some degree of accuracy. There are other applications of sensing specific to health that you've explored that do not require, or are there? So again, there's colleagues like Mayank Gawal at my department that are actually, their whole research avenue is on health sensing or mobile health sensing. So certainly there are people that are very focused on those domains and are experts in those that I wouldn't claim to be. But again, if you email me, I'm happy to point you towards some of those researchers. And certainly if you think about, what we try to show in our projects like Acoustics is, look at all this cool stuff that you could do with this microphone that you've included in smartwatches since V1, and you've never done anything with them except, make kind of Dick Tracy style kind of calls. That's cool, but is there other things that can be done? And so we do a little bit of health, we do a little bit of kind of OSHA style safety, we do recipe helping, we do kids playing with toys, we do people tuning up their guitars. We try to do breadth as opposed to depth to kind of get all these different segments of industry excited. Because at least for me as an academic, the way that we have impact is by getting people excited about technology such that companies like Samsung and Apple and Google have to catch up to kind of consumer expectation. It's very hard, and many of you work in industry, so you know that pain. Taking something from idea to shipping is so painful, and it takes a lot of effort, a lot of time, a lot of tears. And in a research lab setting like mine at CMU, we tend to be more nimble in that rapid prototyping mode, which I know a lot of you do as well. And so we want to influence industry and have them put the 1,000 engineers behind it at Apple by getting consumers excited about the possibilities. So it's in some respects, it's almost like a kind of science fiction prototyping. We're showing what could be possible. Any other questions that I can field from people? And people are welcome to unmute themselves as well.
Hi, Chris. I've actually got a question.
Yeah.
I'm Danielle. So I know you were talking about not having to use wake words, I think you called them, for the machines and devices. And I know you said like you can tell from the direction of your voice or how close someone is standing. Do you know of different solutions, I guess, for, if you're far away from your machine or if there are other people in the house, how will it know that it's actually being spoken to and not another human interaction?
It's a great question. It gets harder, but you can sort of, what I always like to kind of do is like, if I blindfolded you, but like I was like in your kitchen, but you couldn't, like you didn't know where I was, right?
Mm-hmm.
But I said like, hey, you'd probably be able to guess where I was in your kitchen, right? Because you like know that acoustic space so well. And it's, computers, especially for like a HomePod or a Google Home, sitting on that countertop spot, it should really be like a super expert. Like it's the only one that spent, 10,000 hours sitting in that one spot. So I feel like it's totally possible for them to be able to guess range and sort of where you are. And obviously if you walk towards it versus walking away, you can sort of add in some extra logic that a human assistant would be able to do. And then also just picking up context, if it's like multiple people chatting and I say, hey, how's the weather? Or like, it should be able to know I'm in conversation mode. If it's like total silence and then I just blurt out, what's the weather tomorrow? It probably should guess I'm talking to it, right? So, but this is sort of the level of sophistication that humans bring to these kind of problems, and then computers are like 100% dumb at. But it's not unbelievable to think that there's just enough signal there that they could be made smarter. So I'm hopeful that it could be done.
Awesome. Okay, thank you so much.
Okay, yeah. Thank you for that pointer, Jet. Any other questions that I can answer? Okay, well, good questions, everyone. And again, feel free to reach out to me by email if you want to touch base or follow up on any of these topics.
And thank you, Chris. I think I'm speaking for everyone. This was amazing. I learned a ton. Yeah, exactly. We can do virtual claps. So we're so lucky to have you in our backyard. So please reach out and we'll post the recording on our YouTube channel soon. And Allison, if you're still here, do you want to say a couple of words about our next talk?
I'm muted, yes, hi. Yeah, next month we have Catherine Fraser. She is a CMU graduate. She graduated, I think maybe 6 or 7 years ago at this point. And she's gonna be giving a talk. She's really into the Japanese art of flower arrangements. So it's gonna be a talk about software development based on those kinds of rules. And it's really about inspiration and taking inspiration for software development from different places.
Very cool. Yes, that will be on March 25th. We will, of course, send out notifications about it through all different channels. But once again, I want to thank Chris and thanks everybody who showed up. So enjoy your weekends and thanks for being here.
Yep.
See you next time.
Thanks, Chris.
Thank you.
Thanks, everyone. Thanks for coming.
My Zoom locked up again. Chris, I'll send you an email about the stuff I'm working on. Oh, he's already gone.
I think Chris may have left already.
Yeah.
Mine. I worked for him for a year. I know how to find him. See you later.
All right, see you.
Bye, Jet.
All righty. Well, this was awesome.